All right, I hope everyone can hear me. I think we can start. Let me just check if everyone can hear me 1 second. All right, so hi everyone, I'm Anya, I'm business manager of K-Mine. We decided to diversify things a little bit today and basically to create something like a stream/training. So I believe there are a lot of geologists today that eager to see different types of geological modeling that we promised to show you guys. And as usual, if someone that you don't know couldn't make it today and would be interested to see the stream, we always post our recording of the session in our LinkedIn profile and on our LinkedIn page and our LinkedIn page and our YouTube page. So you will actually be able to send them recording of the stream. Basically, if you are interested to know who would be our guest today, that would be our chief geologist, Tatiana Nestenko. But I first want to stop on briefly on our agenda today. It's basically, let me just share my screen real quick. Okay, so basically we will be focusing today specifically on geological modeling and resource block model creation. First, we will start with the database setup in K-Mine as its very first step. And then when it comes to geological modeling, of course, we will cover SIM and cubic block modeling. And for the first time, we will also demonstrate our implicit modeling feature, which will be released to production next month. When it comes to resource block modeling, we will also review various methods of mineral resource estimation and calculations. We just want to remind everyone that we currently have 12 models for open pit and for underground mining. They all can function as a standalone model or in the conjunction with each other. So the part of the functionality that we're going to review today is included only in our geology model. Just to give you an idea how many features we have in general. Well, let's just dive into that. I would like to introduce you our chief geologist, Tatiana Nestenko, who will be actually the main speaker today, and she will demo you the functionality and review different approaches as far as deposit simulation. And please don't forget to send your questions to our chat. We will gather them and we'll try to answer them in the end of the stream. But now I want to give the floor to Tatiana.
Thank you, Anya. So if you guys work with various geographic information systems, you know that when you create a deposit block model there, this function looks very similar to many other applications, like you need to create or import a database, outline the geological differences, create solid wireframe, to perform grade interpolation and create a block model. However, if you do it for a long time, you know that if you create a deposit block model as a part of analysis of the exploration data set, there will always be some research moments. For instance, your research always depends on the mineral type and genetic type of the mineral deposit, and we always have different interpolation options and extrapolation methods. Also, there are different ways of contouring, which is cutoff grade in the sample, block, selective mining unit, and different methods of mineral resources and reserves calculations, like the polygonal method or block estimation. And I'm not even diving deeper into different classifications. For example, United Nations Framework Classification for Resources, CRIRSCO, and national classifications of different countries, Long story short, you need to be very experienced to perform geologic simulation efficiently and correctly. So of course, if the software that you are using is programmed with a superficial understanding of the process, or it doesn't consider all necessary geological processes, you will end up with inaccurate and unrealistic geological interpretation. We always should remember that geological models are often based on the interpretation of core sampling data. So it represents a very small part of the ore body, and that very model determines the next steps in the project development. That's why the geological models are always temporary and their interpretations is never set in stone. We also should not forget that incorrect geological interpretation leads to potential standard errors that can be way more significant than errors associated with content estimation. So the digital database is the foundation for the entire process when it comes to geological, mathematical, and block simulation. It has also established the ground for technical and economic calculations, reserve and resource estimation, and further research with follow-up procedures that ensure the great control systems at mining enterprises. K-Mine uses a relational database model that is implemented in many software solutions like Microsoft Access, Oracle, MySQL, and others. Our applications support these solutions, as very often our clients store their geological databases on a PostgreSQL server. According to the relational database models, the digital geological database consists of tables like the coordinates of drill holes, the Inclinometry drill hole table, which is called survey, and assay or geological description of workings, which would be lithology. If the survey table is missing, then the mine workings are considered vertical. In K-Mine, you can have any number of additional tables or columns with no limits, but at every minimum you will have these three. The required fields in the color table are drill hole number, longitude, latitude, and elevation Z coordinate. For longitude, you can choose X or Y depending on the coordinate system that you selected. In K-Mine, a user can select a Cartesian or geodetic system before creating the project. You can add more fields in this table, like for example, drill hole depth, drilling date, drill hole type, special permit name, profile number, and others. The Inclinometry table stores drill hole deflection information, which is used to calculate drill hole path coordinates and the sample and geological interval coordinates. So in this table, in survey, the required fields are drill hole ID, the depth or distance from the collar to the measurement point, the slope angle and azimuth of the drill hole. All geological information in the database is stored in additional tables, like assay, lithology, spectral analysis, composite, and others. Usually, besides the useful component grades by sampling interval, the sampling result tables can include the additional fields of level and ore body number, drill hole size, core recovery, drift, and others. The rock characteristics are presented as rock codes for the geological interval in the appropriate lithology field of the geology table. Rock codes are contained in the additional table of the rock type guide. When two drifts of surface or underground mine working are assayed, each assay line is created as an individual line starting at the mine working mouth at two different starting points. So when the geological characteristics have the interval length different from the assay interval length, K-Mine creates independent tables. There, the drill hole number would be the main field of the table and the corresponding fields as depths from, depths to. These geological characteristics include overlapping mineralization, gravity, and geotechnical aspects like axial compressive strength, shear strength, and others. Theoretically, there could be as many of these tables as you want, like tectonics, seismology, geophysics. Whenever you need to record any additional geological information, the system creates a separate table. As far as the data entry, users can input their data or upload it directly from an Excel file. In order to do that, you should select the required database and Excel file to import this data. Each table must contain a title bar with field names to see what field and from which column you are going to import into the database. You can also import data from point objects into the database. This can be individual samples obtained from the surface, like sheep samples or tailing sampling. The same way, you can add the points where the mine working starts, like trenches, into the color table, and then fill up a subordinate table of sheep samples that were extracted from the trench walls. When the import process is completed, you need to analyze and verify the source data to eliminate possible mistakes. For instance, errors of primary geological materials can be eliminated with visualization. For example, you can visualize the exploration mine workings and compare them with the corresponding geological map or section. In order to do that, you need to set the coordinate grid and scale and rotate the image if needed. This manipulation might reveal more severe errors in the primary geological materials. However, minor deviations can happen because of the features of used projections, their datum and transfer parameters from one system to another. By the way, user can vectorize the required objects from downloaded images, for example, the regional fault traces under the quaternary sediments. And they can download an image of any format, such as BMP, GPG, PNG, DDS, and others. You can also download a map section from Google Maps or save objects from KMine to KML format. So you can later open it in Google Earth Pro. This way, you can automatically load section boundaries from a polyline objects, then enter the geographic coordinates in decimal format, or if you have a file in CSV format, you can just upload it and display the map. When you input the data and the mine working number is available in the coordinate file, one of the most typical errors is the absence of the assay results in the file. The other one is the existence of a gap between assays. So the sample intervals are not adjacent or they are superposed in each other in the assay result file. You can also get the total drill hole depth in lower than the edge assay depth. And some of these errors can be found during the statistical analysis because it helps you to understand the type of mineralization distribution you are working with, whether it's normal or log normal. Statistical analysis also allows you to determine the heterogeneity of the data set, which can be caused by several generations of mineralization of the variable component. And polygenic heterogeneous sets should preferably be processed and analyzed individually. If the samples are examined for several component contents or by different analytical methods, it is essential to perform a correlation analysis with a regression equation. It is also possible to determine the variation coefficient of grades or thickness. In KMine, you can also automatically merge the sampling and lithology tables into a cross-assay table in case you need to recalculate the values. It might be necessary when the from and to lithology intervals in the lithology table do not match the sampling intervals in the assay table. Let me clarify why this step is so important. Users can store sampling and lithology tables separately. However, there are cases when you must do some calculations directly in the database tables. For example, you need to identify grade intervals by a set of requirements for the mineral quality, or you need to specify the interval assignment to one or another mineral grade by technological properties of ores. In these cases, you can use triggers. They would allow you to create a required combined condition and recalculate the parameters by intervals. For instance, you need to create a condition to determine the content boundaries. So now we create some rows in lithology and assay table, and we get cross-assay. If in the lead ID field, the rock equals 2, for example, now we are writing some new trigger, new formula, and content more than 15% and less than 20%. Then we can input index 2 in column tech grade. In this case, specifically, all the required data like lithology, valuable component grades, and detrimental impurities must be contained in a single summary table. Also, for complex ores, you can recalculate the grades by means of conversion factors and bring them to the conditional grade of the main component. For example, now we can see for ilmenite and sillimanite and sterilite and zirconium. The boundaries of ore bodies would be defined only by the result of the mine assaying. In these cases, we should include different condition parameters like cut-off grade or valuable component or minimum ore body thickness. The other parameter would be a maximum permissible thickness of waste rock interlayers or maximum permissible thickness of substandard ore contained in the ore body boundary. If the ore interval is shorter than defined by conditions, but has a high level of valuable component, we should also consider a minimum metrogram. Minimum metrogram is a result of multiplication of cut-off grade and minimum ore body thickness. In K-mine, we have an algorithm that selects ore intervals according to the consequential additional of the interval. When a conditioned ore interval is being created at the deposit with an intermittent distribution of mineralization, and it's happening in the direction of thickness, the secondary intervals are consequently added to the main ore interval. Taking into account the grades, if the content of a valuable component in the added boundary is above or equal to the cut-off grade, this section would be included in the common boundary of the ore interval. We often use this method for polygonal method calculation. The database also includes algorithms to analyze and calculate average grades of the filtered table data. You can recalculate indicators to the colors table from any sub-table. You can also create point objects in the workspace to construct the roof or bottom surface, to build isolines or descents, polygons. The same way, users can perform statistical analysis by average mine workings in the colors table. For example, average thickness, average grade by mine workings to contour estimated blocks of reserves and resources in the plan. You can also calculate the coefficient of variation of the ore body strike. And of course, when we talk about statistical analysis, we can't skip compositing. Compositing is a declustering method. It ensures the comparability of the influence of samples with different lengths on statistical estimates in the domain. In K-mine, compositing is performed automatically. You just need to create a new table and the required columns in the database structure. The composite table is stored separately from assay, so you can update the table and recalculate the data when a new composite length is selected. Or you can create a set of tables for different conditions at any time. We also have tools to filter the data in the table and compositing within the solids. Compositing changes the statistical characteristics of the component distribution, mostly causing a decrease in dispersion, a change in the average and anisotropy. How the compositing process affects the creation of the block model really depends on the geological structure and the specific of exploration operations on the deposit. So now, since we have prepared the database, we finally got to the subject of today's stream, geological model creation, which would be the next step of the block model creation process. Overall, there are a few ways you can perform a simulation process. In K-mine, now there are 4 methods. You can create a cubic block model, the empty one, without property values in blocks, or you can import it from files with LAS or CSV format. You can also create a sim block model based on the lithologic description of the mine workings in the database. In this type of model, the blocks will have a certain size by X and Y axes. The size of cubes by Z axis would vary depending on the recalculation of row interval thickness in the database. You can also create a cubic block model for sim deposits using lithologic variety codes from the database. All blocks would have a certain size by 3 axes in this model. For example, 10, 10, 1 meter. Finally, you can use implicit simulation using a method of radial basis functions or RBF method. This algorithm includes rock codes or other parameters that can be used in RBF interpolation. Users can choose these parameters and create triangulation surfaces of lithological differences. For explicit simulation, we would create an empty cubic block model in the form of parallelepiped, and we would use triangulation surfaces to determine block attributes and define geological contact boundaries. So if you want to create solids and surfaces, you need to outline the bodies in the plan or section. So to create a new block model, we just need to specify in the name field an ODFB file. In the dimensions field, we need to input the block model sizes and the rotation angles of the axes. And finally, we just need to know that in the block sizes field, the minimum dimensions of blocks by axis. 5, 5, 5, okay. By the way, in the recently updated K-mine version, users can change dimensions and axis. Now you can see axis angles when creating a block model. So you just need to select the rotation axis or vertex with the cursor. And green one, blue one. Within the block model dimensions that were specified at the start point, K-mine will create the largest possible blocks that would be multiple of the specified minimum size. Now you can see new block model. K-mine uses the octree subdivision method. In other words, a regular method of sub-blocking. So that parent blocks must be divided into fractions like 1 second, 1/4, 1/8, etc. This way, the block model is constructed from the largest to the smallest block, starting from the start point. As you can see, the maximum block size is 320 meters, the next one 160, next one 80, and 40, 20, 10 meters, and finally it becomes to 5 meters in this block model. Moving forward, users can sub-block within a solid or the entire model up to any required block size. In other words, a block model can have completely different sizes of sub-blocks in different zones of the model. So users can only divide up to the specified minimum block size. If you want to reduce the block size, then you should create a new block model based on the existing one. So it would facilitate and speed up the process of a new block model creation. The system by default creates a minimum set of block model properties, like the block center coordinates and block sizes along axis, color, and unit weight. If you want, you can add new rows to the property table and specify things like property name, field type, and property value if it's similar to all blocks of the model. After creating a block model, you can sub-block within the specified solid using the setProperties function. You can also transfer a property to blocks within a solid. It could be, for example, a unit weight or work code. To do it, add a geometry row, choose a necessary object for the limitation. There are 4 conditions for the limitation. For solids, equal means inside, not equal means outside, below the surface, and top means above the surface. User can also import a block model from the LAS or CSV file. If you want to import a previously created block model, set up the path to LAS or CSV file in the source data field. After you select a file, you will see the load data dialog box where you can preview the data in the source file. Just set up constraints for integer, fractional parts, and columns. You should also set the header row key to visualize the column names of the imported model when you are setting property correspondence. If you want to upload the data without considering the column headers, just set the value of 1 in the field load rows. After that, you can configure the correspondence between the properties of the imported and created new block model. You can also add additional properties to the created block model, add new rows to the property table, specify the property name, field type, and property value if you want to. The block model will be stored as a separate file in the path that was specified by a user and as a graphical object in the layer editor of the current ODF file format. So the current ODF file can store several block models in the layer editor, and each of them has an individual ODFB file. If you move an ODFB file to another folder, you just need to set up a new path to it when you open the ODF file format. As I mentioned before, you can also create a new block model based on a previously created one. For example, that would be the case if you want to change the minimum block size or add additional model properties. If you change the block size compared to the original block model during the import process, you can easily recalculate the property values in the blocks. Like on the video, we are creating 12 meters blocks to 10, 10, 7 meters. You can recalculate these values using weighted average by volume, weighted average by weight, or maximum weight. If the new block model is bigger than the imported one, The additional empty blocks will be created with a lithology code of 0. So now we can see blocks. We make visible only blocks with the code not equal to 0. And now we set visible only the blocks of ore bodies. And you can see that parameters changed. The new block model has dimensions 640, 640, and 448 meters. And this size value is multiple of 10, 10, 7. That was set when you created a new block model. If you want to filter blocks of a block model, user can use conditions, fractions like equal, less, greater, between, contains, etc. For example, let's visualize blocks with content of more than 25%. In this row, firm total, 25, okay. Or 35, or 40. After that, we can perform the required calculations or change other properties of these blocks. In the case of seam simulation, and the next one, a cubic or seam block model is created within the tectonic block solid. Today, we are not going to consider the process of creating the seam model in detail, as our last stream was dedicated specifically to this subject. So you can go to our YouTube channel to see that video. However, I do want to briefly remind you of the main features of creating a seam block model. We just need to register the chronological sequence of seams and, if required, index the individual alternations when splitting seams. Then we add the alteration intervals of enclosing rocks to the reference table. We just need to remember that each interlayer must have its own unique code. When you are defining all mineral seams and enclosing rock interlayers, choose the surface where the seam model will be automatically constructed. In order to limit the block model, we need to construct a wireframe of overburdened surface, oxidation zones, and other specific surfaces that are limiting the mineral seam. Also, if you create a block model of a complex tectonic structure, we do need to create the limiting boundaries for each tectonic block. You can guarantee the smooth seam block model if you specified each possible seam intersection for calculation and construction. The same goes to calculation of various block parameters. When creating a seam block model, we can specify the number of adjacent drill holes that are involved in the calculation of thickness. In the simulated area does not have any tectonic dislocations or individual modules, all the seams would have one marker surface. So we are creating attributes for the block model: code, zones, category, ash content, moisture content, lower calorific value, and etc. When we create a seam block model, we need to specify block sizes by X and Y axis, and limit the minimum block size by Z-axis. So block sizes by Z-axis range depending on the seam intersection thickness of a particular seam. If you simulate the deposit with tectonic dislocations, the marker surface should be created separately for each tectonic block. Interpolation data analysis of vertex height in marker seam will be done within the solid of each tectonic block. Same way, you can create a cubic block model, cubic seam block model. The difference would be in the block shape. The blocks have different heights by the axis in the seam model, and the blocks by the axis are of certain size in the cubic seam model. When you create this type of block model, you need to set up a correspondence for a new list of lithological variations. You can also assign several varieties to the same rock group from the source reference table of themes or rock types. If the block contains several lithological varieties of low thickness, meaning the thickness would be less than the block height, you would be able to calculate their volume using the percentage ratio. So we have constructed a block model. If this cubic block model is empty, we need to specify the lithological differences, domains, and ore bodies in the block properties. You can do it using wireframes and solids. The simulation process of wireframes and solids depends on the selected method. The new K-mine version has implicit and explicit simulation. So now we can see implicit simulation. Implicit modeling is the fast and automated creation of surfaces directly from the database. It involves creating triangulated surfaces using the method of radial basis function. Implicit modeling allows you to generate ore bodies from the same dataset fast. It also gives an opportunity to use secondary data sources in the geological modeling process, in addition to drill hole intersections. These datasets can include geophysics, spectral drill samples, and mine face scans. So what before was only possible with manual slow digitization, like modeling of complex shaped geological surfaces, can now be done semi-automatically. However, implicit modeling cannot be applied in all the cases. It's not a Swiss knife or block modeling. And that's why for a long time, K-mine didn't include in its set of tools. For example, at the early stage of deposit exploration during the pre-feasibility study, when you have a widely spaced grid of drill holes, you often have to use explicit simulation, which is geological structure interpretation and contouring of ore bodies in the cross sections. Just because a geological volume model is created with an implicit modeling tool does not mean that it is any better or worse than a geological volume model created with any other modeling tools. Both explicit and implicit can be useful models. Both can also be used wrong in wrong experienced hands. However, recently we observed a particular trend on implicit modeling that resulted in many requests from our clients for this functionality. That's why the company decided to implement it in our set of tools this year. And if you want to create a solid, you need to select a code from the reference table in the database. And then select the boundaries for construction. In addition, let's specify the step. For example, lead ID, and we select some rock code in this case. And now we specify step to construct a triangulation grid. For instance, radius to smooth the solid surface, for example, is 250. In the layers field, we need to set the number of iterations. Then we need to set the value to indicate the degree of surface alterability at the peripheral zones. Now we name the layer and set the color and fill the template, apply. The ore body shape will be different from the solid built by triangulation method using a set of cross-section, of course. You can interpret the configuration of the ore body differently while you are creating the ore body projection in the cross-section plane. So we need to create a guideline and merge a set of cross-sections into a closed surface. You can also build solids automatically based on the set of geological contact boundaries on the cross-sections and planes. In this case, the system will take into account their actual intersection by mind working in space. Now let's compare the geological body shape created by the implicit and explicit simulation method. We just need to change the color to dark blue. And the main advantage of implicit simulation is speed. That allows you to perform hundreds of construction actions just by changing some parameters of the simulation. You see how by changing the radius, the bodies change their shape and get divided into separate small deposits. If the radius increases, the construction process of large thickness bodies is continuous. Now again, we change radius to another one. For example, 100. I think that the quality and accuracy of the model depends more on the precision and strict control during the source data gathering stage. Also, a very important role plays the understanding of the deposit structure and experience, of course, of a person who actually creates the model. And we change the color, change radius, and we can see a difference between these three implicit models. K-mine also includes tasks for solid and wireframe intersecting, splitting, and merging. When you create solids, the existence function of extruding the solid from the polygon or wireframe at a specified distance and angle can come handy. Solids are created automatically during the process of ore body bifurcation. Now we can see how to extrude some solid. Sometimes happening when the body or stratum are divided into separate structures and then merged into one body. This phenomenon is called trouser legs because of the shape ore body is divided into. So we can see how to do it automatically, ramified triangulation. There are essential functions to edit and validate wireframes. For example, you can add or delete triangles or vertices. When you create a geological model, all these tools help clarify the shape of geological bodies and increase the reliability of your decisions. Now let's talk about the difference between the geological model and the resource model. One of the most frequently asked questions when reviewing the reports on mineral resources and reserves calculation is, how did you select the cutoff grade? Or why is there such a big difference in the calculated reserves of the proved and probable categories compared to the reserves indicated in the legal documents of the enterprise, like the user permit or mineral resources? If it's a deposit with a simple structure and clear geological boundaries, the modeling is really a simple construction of ore body solids or wireframes. The ore of different properties like technological types, grades, and other varieties are distinguished as separate domains. If there are no strict geological boundaries, in order to outline, mineralization, you should use the condition parameters in a polygonal method. One of the main parameters is a minimum grade in the age sample. It is not cutoff grade for block estimation. This parameter is used to contour the thickness of the ore bodies. The other parameters include maximum thickness of the waste rock interlayers and off-grade ores, minimum ore body thickness, minimum commercial content in the calculated block, and minimum content in the drill hole in order to contour in the plan. Sometimes the parameters of ore grade ratio and metre percent are also used. Block modeling on objects like that is often performed in mineralization zone solids. Then we calculate the ore waste correlation considering the valuable component content in the model blocks, the so-called cutoff grade. The notion of cutoff grade in the method of polygonal reserve calculation refers to a sample in a drill hole or other mine working. Block modeling considers the block contents that frequently cannot be equal. Samples and elementary blocks are characterized by different sizes, which predefine different parameters of statistical distribution on them, including dispersion and asymmetry indices. Within a single solid, the average contents of the samples and blocks can be almost equal. If we divide these statistical groups into ore and ore-free by the same value of the boundary content in the samples and blocks of the model, we get a systemic difference in the estimation of the ore average grades. The magnitude of this offset under the same initial conditions will depend on the natural features of the object, the type of geostatistical model, its parameters, the cutoff grade level limit, the density of the exploration grid, and the conditions to select a mineralized zone or calculated volume and other factors. It is almost impossible to implement directly within the block model such a conditioned indicator like a minimum content per edge intersection. It can be considered only when the preliminary ore body solids are constructed, and they exclude these intersections from the calculation. Now we can see two cases, how to create these different solids shape. In the standard calculation parameters, like the minimum thickness of the ore body and the maximum thickness of waste rock and off-grade or interlayers, are selected considering geological features of the object and a possibility of open pit or underground mining. Theoretically, the value of these parameters can be regulated by the sizes of elementary blocks, but in reality, that is not always the case. The challenges appear with the minimum Metrogram parameter. If there are low thickness intervals with relatively high contents, they are included in the calculation by a standard method. In this situation, the calculation assumes that the Metrogram value is sufficient and initial artificially low thickness is taken into consideration. During the process of block modeling, the contents will be automatically recalculated to the installed composite thickness and will actually be diluted compared to the polygonal method. In the polygonal method calculation of ore body reserves for underground mining, the notion of minimum commercial content is used to divide them by balance sheet attribution that is set according to the estimated block. The ore volume in such a block can sometimes represent an annual production volume. And according to the minimum commercial content, the entire volume of ore can be excluded from the calculation of balance reserves and transferred to the non-commercial class code. As a result, the calculation of mineral resources and reserves in the polygonal method is conducted within the specified commercial boundaries of ore deposit. Now we can see comparing for volume by prism, polygonal method, and by solids. Contouring is used to draw the boundaries of commercial ore reserves, separating them from off-balance sheets and ore hosting rocks. And as we can see, polygonal method in this case give us some volume more than solid volume, but average grade less than in solid model. So, and we can see some volume and average value without cutoff grade, and for blocks above cutoff grade, 25%. Off-balance reserves are calculated in a case when the feasibility study of conditions has proved their preservations in the subsoil for future extraction or practicability or of associated production, storage, and storage for future use. So we have a lot of different tasks for calculating for polygonal method and block estimation methods. Today, when we talk about digital assistance in the mining industry, we often talk about new technologies that can be used in the process. And however, each new know-how always takes into account and geological modeling as one of the cornerstones of exploration processes. One of the main advantages of K-Mine is that we do not implement solutions that are meant to be applied in theory. We always try to solve specific challenges for our clients. And on the high level, it means increasing the quality of ore preparation and decreasing time on the audit of geological data. Most of our successful projects are done because we enhance the automation of data processing and analysis of operation estimation. And today, our existing tools allow you to increase the reliability of reserve estimation on every step of the mining process and decrease the risks on the decision-making process. If you have any question, please.
All right, thank you so much, Tatiana. Well, we'll see if we have any questions here. All right, so one of the questions was how K-Mine is different from Vulkan or MineX. Tatiana, do you hear me?
Yes, Anya, I'm here.
Yeah. So, I mean, one of the questions was, what is the difference and how K-Mine is different from Vulkan or MineX?
Oh, okay, thank you. Actually, there are lots of differences. For example, we can automatically create the structure of the geological database, which simplifies the process of its creation and reduces the time significantly. Our software is much more flexible, customizable, and affordable.
And if you compare it to, let's say, SURPAC block modeling, how our modeling is comparable in this sense?
K-Mine allows you to create block models with a larger number of blocks and more detailed than SURPAC. And we also have a specialized block model for reservoir fields. Also, our block model also supports property lists, which can simplify and speed up the processing of a box model that contains text data.
Okay, great. And the other question was, I mean, I do believe that you mentioned that what type of interpolation algorithm is used for the implicit modeling. We're using radial basis function, correct?
Mm-hmm, yes.
Okay, perfect. One of the questions was, is your methodology acceptable when submitting economic assessments to NI 4301? So that's basically one of the formats that usually required in Canada, and we're actually working with different economic assessment types. We do not have experience with this specific format, but we actually our software actually can be used for this assessment specifically.
Is it just about requirement for some standards from the some standards?
Yes.
We can create some new reports templates for every enterprise, and for every client we have different templates. That's why we have a lot of instruments and functions to have individual reports.
And another question is, do you support some sort of mine hierarchy? I do believe the person meant like tree type of structure.
Yes, we have a flexible structure for working with data by storing information in a tree of layers in our layer editor.
And the other question is, what are the attributes that you support in your mining blog?
Any indicators can be recorded in the BM attributes, including those. Mostly it could be block coordinates, block sizes, rock density, weight, rates, rock types, and etc.
Okay, great. So I think that was all as far as the questions. You feel free to send more questions to our LinkedIn page or to this chat as well. We will just answer it after the stream. I think just want to mention one more time that we will release this functionality next month. And so if you're interested to try it out, please contact us. You can email us to hello@kmine.com, or you can send us just a note to our LinkedIn page and to the chat, and we will get back to you. I think that's it. Thank you guys so much for joining, and thank you for Tatiana. Thank you for your time. Again, we will send you the recording of the stream. We will post it on our YouTube channel and our LinkedIn page. So please follow the updates. And I guess we will see everyone next year. Well, thank you so much. Bye, guys.
Happy New Year.
All right. Bye.